The National Electrical Code (NEC) does not explicitly limit the number of 90-degree bends in the cable tray run. However, there are indirect requirements that must be considered. Article 392.10 states that cable trays must be installed to support and protect the cables within from physical damage. Article 392.10 specifies that cable trays must be protected from the elements and mechanical damage. An inspector may interpret these requirements to mean that excessive 90-degree bends could compromise the support and protection of the cables. This is a reasonable interpretation, as sharp bends can put stress on the cables and make them more susceptible to damage. Although the NEC does not specify a limit on 90-degree bends, industry best practices generally recommend limiting the total number of bends in a cable tray run to a maximum of 360 degrees. This is because excessive bends can firstly increase friction on the cables, making it difficult to pull cables through the tray, secondly, damage the cables by crushing or pinching, and thirdly, inhibit proper cooling and ventilation of the cables. In addition to the code requirements and best practices, there are practical considerations to keep in mind when designing cable tray runs. Cable trays have a minimum bend radius that must be met to prevent damage to the cables. The number of bends in a tray can affect the cable fill and the amount of derating required. Excessive bends can make it difficult to access and maintain cables within the tray. While the NEC does not explicitly limit the number of 90-degree bends in cable tray, it is important to consider the potential impact of excessive bends on cable support, protection, and maintenance. Best practices generally recommend limiting the total number of bends to 360 degrees. The inspector's interpretation may have been reasonable based on these indirect requirements and industry guidelines. Considering the mechanical stress on cables, exceeding the recommended bend limits introduces stress points, which, over time, may lead to insulation breakdown or conductor damage. The repeated bending and straightening of cables, especially during installation or maintenance, can weaken the conductors, increasing the risk of failure. Secondly, excessive bends can obstruct airflow around the cables. Overheating can accelerate the degradation of insulation materials, reducing the lifespan of the cables and increasing the risk of short circuits or fires. Thirdly, sharp bends make it more difficult to add, remove, or reroute cables within the tray. In tight spaces, maneuvering cables around numerous bends can be physically challenging and time-consuming, leading to increased labor costs and potential damage to the cables during handling. The fill capacity of the cable tray is impacted. Excessive bends reduce the available space within the tray, making it more difficult to achieve proper cable spacing and potentially leading to overcrowding. Overcrowding can exacerbate heat buildup and increase the risk of cable damage due to abrasion or compression. The impact on derating requirements. When cables are bundled or closely spaced in a cable tray, their ampacity, current carrying capacity, must be derated to prevent overheating. Excessive bends can contribute to increased bundling and reduced airflow, necessitating further derating of the cables. The bend radius of cable trays is a critical factor in maintaining the integrity and performance of the cables they support. The minimum bend radius is the smallest radius that a cable can be bent around without causing damage to its conductors, insulation, or shielding. Adhering to the manufacturer's recommendations for minimum bend radius is essential to ensure the long-term reliability and safety of electrical systems. Firstly, conductor damage. Bending a cable too sharply can cause the conductors to stretch, compress, or even break. This can lead to increased resistance, reduced current carrying capacity, and potential failure of the cable. Secondly, insulation damage. Exceeding the minimum bend radius can compromise the integrity of the insulation, creating weak points where moisture, contaminants, or electrical stress can cause premature failure. Thirdly, shielding damage. Shielded cables, such as those used for data communication or instrumentation, are particularly susceptible to damage from excessive bending. The shielding can become distorted or fractured, reducing its effectiveness in protecting the signal from electromagnetic interference. The NEC guidelines are for minimum bend radius. Article 300.34 addresses the minimum bending radius for conductors. Although it doesn't explicitly specify requirements for cable trays, it provides general guidance applicable to all conductors. Specific cable types may have their own minimum bend radius requirements specified in their respective articles within the NEC. Firstly, manufacturer specifications. Cable manufacturers typically provide detailed specifications for their products, including minimum bend radius requirements. These specifications should always be followed to ensure the proper installation and performance of the cables. Secondly, industry standards. Organizations such as the Insulated Cable Engineers Association (ICEA) and the National Electrical Manufacturers Association (NEMA) publish standards and guidelines for cable installation, including recommendations for minimum bend radius. These standards can provide valuable guidance for installers and designers. Thirdly, practical considerations. In addition to code requirements and industry standards, practical considerations should also be taken into account when determining the appropriate bend radius for cables in a cable tray. Factors such as the type of cable, the installation environment, and the available space should all be considered. Several types of cable tray bends are available to accommodate different changes in direction. These include horizontal bends, vertical bends, and offset bends. Horizontal bends are used to change the direction of the cable tray in the horizontal plane. They are typically available in standard angles such as 30 degrees, 45 degrees, and 90 degrees. Vertical bends are used to change the direction of the cable tray in the vertical plane. They are also available in standard angles such as 30 degrees, 45 degrees, and 90 degrees. Offset bends are used to change the elevation of the cable tray while maintaining its horizontal alignment. They are often used to route cable trays around obstructions or to connect trays at different elevations. The cable fill in cable trays refers to the amount of space occupied by cables within the tray. Proper cable fill is essential to ensure adequate ventilation, prevent overheating, and facilitate maintenance. The NEC provides guidelines for cable fill in cable trays in Article 392. These guidelines specify the maximum allowable fill based on the type of cable tray, the size of the cables, and the number of cables in the tray. The NEC specifies different fill requirements for solid bottom cable trays and ventilated cable trays. Solid bottom cable trays, also known as non-ventilated cable trays, have a solid bottom that restricts airflow around the cables. As a result, the allowable fill is lower than that for ventilated cable trays. Ventilated cable trays have openings in the bottom that allow for better airflow around the cables. This allows for a higher fill percentage compared to solid bottom cable trays. The NEC provides specific formulas for calculating the allowable cable fill in cable trays. These formulas take into account the cross-sectional area of the cables and the dimensions of the cable tray. The ampacity of a conductor is its current carrying capacity in amps. When multiple conductors are installed in close proximity, such as in a cable tray, their ampacity must be derated to prevent overheating. The NEC provides tables and guidelines for derating conductors in Article 310.15 and related tables. The derating factors depend on the number of current carrying conductors in the tray, the ambient temperature, and the type of insulation. The number of current carrying conductors in a cable tray is a primary factor in determining the derating requirements. The more conductors in the tray, the greater the heat buildup and the more significant the derating. The ambient temperature also affects the ampacity of conductors. Higher ambient temperatures reduce the ability of the conductors to dissipate heat, requiring further derating. The type of insulation used in the conductors also affects their ampacity. Some insulation materials are better at withstanding high temperatures than others, allowing for higher ampacity ratings. Proper installation practices are essential for ensuring the safe and reliable operation of cable tray systems. These practices include properly supporting the cable tray, maintaining adequate spacing between cables, and avoiding sharp bends that could damage the cables. Cable trays must be properly supported to prevent sagging or collapse. The support should be spaced according to the manufacturer's recommendations and should be securely attached to the building structure. Adequate spacing between cables is essential for promoting airflow and preventing overheating. The NEC specifies minimum spacing requirements for cables in cable trays. Sharp bends in cable trays can damage the cables and reduce their current carrying capacity. The NEC recommends using gradual bends with a radius of at least 6 times the diameter of the cable. Regular inspection and maintenance are essential for ensuring the continued safe and reliable operation of cable tray systems. Inspection should be conducted periodically to check for signs of damage, corrosion, or overloading. Maintenance tasks should include tightening loose connections, replacing damaged cables, and cleaning the cable tray to remove dirt and debris. Signs of damage to the cable tray, such as cracks, dents, or corrosion, should be addressed promptly to prevent further deterioration. Loose connections can cause overheating and electrical hazards. All connections should be checked periodically and tightened as necessary. Damaged cables should be replaced immediately to prevent electrical hazards and ensure the continued reliable operation of the system. Dirt and debris can accumulate in cable trays, restricting airflow and contributing to overheating. The cable tray should be cleaned periodically to remove any buildup of dirt and debris. Proper grounding and bonding are essential for ensuring the safety of cable tray systems. Grounding provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock hazards. Bonding ensures that all metal parts of the cable tray system are electrically connected, reducing the risk of voltage differences that could cause electrical shock. The NEC specifies requirements for grounding and bonding cable tray systems in Article 250. The cable tray itself should be grounded to provide a path for fault current. All metal parts of the cable tray system, including the tray sections, fittings, and supports, should be bonded together to ensure electrical continuity. Grounding and bonding connections should be made using approved methods and materials, such as grounding clamps and bonding jumpers. The type of environment in which the cable tray system is installed can affect its design and installation requirements. For example, cable trays installed in corrosive environments may require special materials or coatings to protect against corrosion. Cable trays installed in hazardous locations may require special enclosures or seals to prevent explosions. In corrosive environments, such as those found in chemical plants or coastal areas, cable trays should be made from corrosion-resistant materials such as stainless steel or aluminum. Alternatively, the cable tray can be coated with a corrosion-resistant coating such as epoxy or polyurethane. In hazardous locations, such as those where flammable gases or vapors are present, cable trays must be installed in accordance with the requirements of Article 500 of the NEC. This may require the use of explosion-proof enclosures, seals, and other special equipment. Considering future expansion when designing cable tray systems is essential for ensuring that the system can accommodate future growth and changes. This may involve selecting a cable tray size that is larger than currently needed, or designing the system with additional supports and mounting points to allow for future expansion. Leaving extra space in the cable tray allows for the addition of new cables as needed without overcrowding the tray or exceeding its full capacity. Designing the system with additional supports and mounting points makes it easier to add new sections of cable tray or reconfigure the existing system to accommodate future changes. Documenting the cable tray system is important for facilitating maintenance, troubleshooting, and future modifications. The documentation should include a detailed layout of the cable tray system, as well as information on the type of cable tray used, the size and type of cables installed, and the grounding and bonding connections. A detailed layout of the cable tray system can help technicians quickly locate and identify specific cables or components. Information on the type of cable tray used, the size and type of cables installed, and the grounding and bonding connections can be helpful for troubleshooting problems or making modifications to the system.